Okay, so previously we did the method of sections, and in that video we calculated the reaction forces as well as the free forces through this section over here. So ED, EH and GH, and those forces can be seen over here, and the reaction forces over here. So I'm not going to calculate them again. We're going to do the method of joints now, and then we can compare the method of sections with the method of joints for these three forces. Alright, so let's first set up a sort of table for all the reaction forces that I want to calculate, and then we can fill it in as we go along. So for this guy, I'll link the previous video where we did the calculations for the reaction forces and for the section. I'll link that in this description below, so you can go and watch that, and then come back to this guy if you are more interested in method of joints and would not want to see how we calculate that, but do want to see how we got the reaction forces. Then you can go ahead and watch that first. Alright, let me set up a table for us. So what we want is we want FAB. I'm going to work my way up from A all the way to the top. We want to know what that is. We want FAI. I feel stupid that I laughed at that, but alright. And then FBs. FBC, FBI, okay, now FC has 3. Okay, I think we should tick them off as we go along. We got that one, we've written down this one, this one, this one we've got, this one we've got. Okay, FC. This guy. Our 3 C forces. FC, FC, FCD, FCH, and FCI. FCD, FCH, and FCI. Okay. So now we have this guy, and this guy. And then FD, we need 2 more of those. So FD, also from that, and it's FDE and FDH. That looks kind of like a B. Let me redo that D. With the method of joints, you really got to make sure that you don't get confused. So it's good to double check everything. So now we have this guy, and we have this guy. Now it is 3 forces for E, E, F, E, G, and E, H. Okay. F, E, F, F, E, G, and F, E, H. Okay, that is all the forces. Let's count them. The reason now why I want to quickly go and count them, just want to make sure that we'll get enough equations to solve all these. We should, because this is a problem that I pulled off the internet, but let's just, okay, maybe I should not count and talk at the same time. This is a 6, 7, 8, 9, 10, 11, and 12. Okay, and I have now, we're missing one force, I see now. There's E, 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 and then there's F, G, and G, H. We missed those two. So I'm going to quickly, that's why we need to double check all these things, F, G, and G, H. F, G, H. Now we should have all the forces. We see there's 13, 14 members that we want to go calculate. Great. I'm going to quickly tick them off as well. Okay, I've written all of those down. Oh, we're missing another one. Keep on getting more. All right, this guy. H, I. Okay, do we have all of the forces now? This one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Great, it seems like we have all of them now. And how many joints do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 joints. So for every joint we're going to get two equations, so it's 9 times 2, because we can't get moment equations now. We can only get sum of forces in x and sum of forces in y. Moments don't work if it's all at one point. You can't have moments then if all of the forces goes through that single point. So there are 18 equations and we want to calculate 50 forces, so we have more than enough equations for the amount of forces that we want to go calculate. So great, that is fantastic. Now, next thing we need to do is we need to start setting up free body diagrams. And I essentially want to set up a free body diagram for each point, but I don't necessarily have to do that. So I'm gonna remove all of these. I'm just going to set up enough free body diagrams for each of these points, so I can get every single equation, but no more than that. So I'm going to have to make sure that I do not need to calculate more than 2 per equation that I set up. So I'm going to set them up in sequence, and I should not have to calculate more than 2 forces or 2 members' forces for each point that I'm looking at. Otherwise I can't solve that in one go. Then I have to do multiple equations and solve them simultaneously, and that's just well, that gets really nasty really quickly. So I don't want to do that. So I'm going to take point A, have a look at point A, and I'm just going to write the points that I want to set up next to here. And if I look at point A, there's 2 members and then the reaction forces, so I can go calculate this one and this one. And then I will also set up one for point B. And there's 3 more members at point B, but when I go from point A to point B, I've already calculated AB, so then I just have to calculate BC and BI. So that's good, I can do that. Then let's do one for point I, because I have now IB and AI, so I can set up, I just now have 2 members left that I need to calculate. That's HI and IC. Great. And now I can move over to point C. For point C, then I just have to calculate DC and CH, because IC or CI and BC I have already calculated, so I need that one. And okay, then I'm going to go to point D, because from point D I just have 2 members that I still need to calculate. And then I think I'll go to point H, because then I can calculate this member, this guy, and oh, very nice. That's nice. You see something here is we actually do not need to calculate all 15 of these forces because we can argue about some of them. And that is that EG will be a 0-member force. And because the reason for that is when you look at the free body diagram, and we now again assume that all of the forces are in tension, or that tension is positive and compression is negative. So we do our free body diagram assuming all tension forces, and this guy, all the forces needs to be aligned with the members, because these are 2 force members. They cannot have forces to the side, otherwise they would want to spin. The only way these things can be in equilibrium, because they only have 2 points of connection, is if there are 2 force members. And for a bar or a beam or something like that, the only way it can be a 2 force member is if the forces are aligned either in compression for that member or away from that member. So it can either be in compression or in tension. It cannot be in anything else, at least for truss systems. So this needs to be true, and this needs to be in equilibrium. The problem is that EG is 90 degrees away from both GF and GH. So these 2 forces have no impact on EG. So EG is the only force acting in the Y direction. And for that to still then be in equilibrium, if EG needs to be 0. Otherwise, this thing cannot be in equilibrium. And we know it is. So we already have our first force, EG, as we go. EG is 0. So we already have our first force. Great. So I can tick that one off as well. We do not have to go calculate that anymore. Okay, and then the only one left, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What am I missing? 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. Do I have 13? This is a group of 5. This is 3. 3 plus 5 is 8, it's 12. I feel like I'm missing a member. There should be 15, right? Which one am I missing? Or did I not calculate that correctly? Do I have a double force somewhere? Hmm. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, I have 15. So then why did I only calculate 12? counted 12 tick marks. This is 5 here. 6, 7, 8, 9, 10, 11, 12, 13. Okay, now there is 13. I miscounted. Anyway, and then the only other one I need to set up is F, because then I can calculate this guy and this guy. And then I do not waste more calculations than I have to. All right. So these are all the points that I need to set up a free body diagram for. Okay, let's get started. Let's get cracking with point A. And point A, I'm going to draw all of these. No, I'm still going to do it like this. And then I'm going to put the members in tension. So in tension, they always pull away from the point. And all of these have I'm going to go with this axis system. And it is 2 meters away, 1.5. But in the previous video, we discussed that these are just ratios. So I can set them up as a 4. And a 3, I times them by 2, and then this is the nice triangle that you were introduced to all the way back, way back in school. We know this side is going to be 5 in length. So now we have the angles, and this guy, I'm going to just put in the value for the reaction force. It is a Y, and that is 32.5. Kilonewton, and then we have another one. This is RAX, and RAX is 70 kilonewtons. No, I messed that up. I should do them the other way around. This guy is 32.5 kilonewtons, and this guy in the X direction is 70 kilonewtons. Should be correct now. 70 kilonewtons in the X direction and 52.5 in the Y direction. And then we have FAI. And FAB. Okay, our first free body diagram. And now we are going to do sum of forces let's do sum of forces in X direction first, because there is, and I need to keep on defining the direction just to make things clear, because you can see that FAB is the only force that I don't know which has a component in the X direction. So X direction equals to 0. And then we have 70 kilonewtons plus, because this one is also in the positive direction, and it is 4 over 5 FAB. Okay, great. And then FAB is going to be equal to, we move that over, and then we see it is going to be a negative force, and it is 5 over 4 times 70. And then we get minus 87.5 kilonewtons. And we see this one is a compression force. because it's negative, and we assumed that it was going to be in tension, so we assumed tension was positive, and we got a negative, so then it's a compression force. And it makes sense, because if we look over here, and I'm going to keep doing that because this is critical in engineering, is if what you see doesn't make sense with what you calculate, you need to question your calculation because it might be wrong. And it often is, but it makes sense in this one because FA is not entirely aligned in the x direction, but it needs to resist a 70 kilonewtons. And we see that the arrows both point in the same x direction. So FA obviously needs to be in the opposite direction. We assumed the wrong direction, so it needs to be negative, and it needs to be larger than 70 kilonewtons because it's not entirely aligned with the x-axis, but it still needs to resist the 70. So then it needs to be larger. And that's exactly what we got. A negative value that is larger than 70. So it makes sense. Great. And now we go on to the second one, and we're going to do sum of forces in the y direction is equal to 0, and we specify that upwards is positive, and then we get the 32.5 and then plus 3/5 FAB and plus FAI. Okay, then the way we go about this one is we need FAI alone, and it's already positive, so we keep it on the same side, and we move these two to the other side of the equation. Then we get negative 32.5, and we sub FAB into that unknown we have over here. So then it is also negative 3/5, and this is really important to keep on checking your signs, times negative 87.5. And then it's FAI and we can quickly go calculate that. 52.5 minus, and I need to keep on checking my signs. And then we get a value of 20 kilonewtons. And let's just check. It should be in tension. Let's go check if that makes sense. Okay. We see that we have a force that goes upwards, and FA also goes upwards, and FAB also goes upwards. But we actually know that FAB should be in compression, so it is in the wrong direction. So it, in fact, goes downwards. Let me just remove that. In fact, it goes downwards. And FAB is significantly larger than the 32.5 kilonewtons, even though it's component-driven. So there's a good argument that the value for FAI should be relatively small, quite possibly positive, because if we just check, we take 3/5 of FAB, that's 87.5, then we get 52.5, so it is 52.5 downwards, and it is 32.5 upwards, so FAI definitely needs to pull upwards as well, so it should be in tension, but it should be a relatively small value compared to the other forces active here. So that makes sense. Okay, now that we trust these values, now I can go and write them down in my little table of sorts over here. No, there we go. So FAB is 87.5 kilonewtons in compression, and FAI is 20 kilonewtons in tension. Great. Now I should definitely write this guy down as point A, otherwise we are going to get confused. So point A is finished. Let's go over to point B now, and I'm going to go a little bit downwards. And point B, let's see, what kind of forces do we have? We have one force that goes upwards. We have another one that goes sideways. And we have that one that we just went and calculated over here. And we already know that it is 4 in the x direction, 3 in the y direction, and then the total length is of 5. Okay, and it is the force FAB. And I'm going to write its value down here so we don't have to keep going back upwards. It's 87.5 kilonewtons. Okay, let's quickly check. This is BI and then BC. FBI, and then this is FBC, and I think we also have another force over here. I just have to check its value, but I think it is 30 kilo, no, it's 40 kilonewtons. 40 kilonewtons. Okay, great. And this one is relatively easy because all the forces that we want to calculate are nicely aligned with the axis system that we chose. So I'm just going to go from x to y. So sum of forces in the x direction is 0, and we defined x this way. And oh, I just need to quickly go and put this is point B, so we don't get confused. And then it is a negative value, negative 40, because it pushes in the negative x direction, minus FBI, and then minus x direction, so that's 4 over 5 AB. I should not put the B first. Let's keep the order that we chose, AB. Okay, and this all, I forgot, this all needs to be equal to 0. Then we have FBI is equal to, and we see that it's negative. We don't want to calculate the negative value of FBI. We want to calculate it as we specified it over here, so we move this to the other side, so we keep these two the same. So this is going to stay minus 40 and minus 4 over 5, and now we're going to sub in the value for that, and it's negative 87.5. Great. And then we can get the answer for that. So it's 40, minus 40, sorry. Minus 40 minus 4 over 5 times minus 87.5. So we get a value of 30. And this will then be in tension. Okay, let's go quickly and look if that makes sense. We have a 40 kilonewtons pushing against. Now I just have to check. Did I take that as correct? Yeah, that's 2 on this one. Okay, so the triangle over here is correct. Great. Okay, we have 40 kilonewtons pushing in the negative direction. Then we have FAB, but we know it's actually a negative value. So it's in fact pushing in the positive direction. And 3/5 of 87.5 is a lot larger than a half at least of that. So it's larger than 40 kilonewtons in the positive direction. So FBI is definitely in the correct direction for equilibrium because it needs to pull away from FAB, which is larger than this 40 kilonewtons. And we expect a relatively small value, so, well, relatively small. 30 kilonewtons is large, but smaller than the other values we already have specified over here. So it all makes sense thus far. And so, yes, 30 kilonewtons seem to be correct in tension. Great, so we trust that one. Next one. So sum of forces in the y direction. And this is going to be equal to 0. And the first one that we have is pulling away from it. So FAB is pulling away, and it is a magnitude of 3/5 times FAB. And then we have one in the positive direction, that is FBC. Okay, we rearrange things to get FBC alone, and it's going to be equal to -3/5, but we swap that to the other side, so I made a mistake here. It's actually now a positive value, and the value of this guy is 87.5. And then we get FBC is equal to 3/5 times -87.5. So we get a value of -52.5 kilonewtons. And this one is then going to be compression. Okay, let's quickly go check if that all makes sense. We have FAB, which is pulling down, but we know that the sign is wrong, so it's actually pushing up. But FBC is also pushing up, so its sign must be wrong. So it needs to be in the negative direction, but it needs to be in compression, but it needs to be smaller than 87.5 because FAB does not entirely pull in the y direction. So we get a smaller compression value than 87.5, so that makes sense to me. Okay, so I trust these values then, and I'm quickly going to write them down. So then we have FBI is 30 kilonewtons in tension. And then we have this one is 52.5 kilonewtons, and this one is compression. Okay, good so far. So now we have B. I am now actually going, it's a little bit sad, but I am going to do it because we are running a little bit out of space. So no. We need to verify these equations with these guys first. So I'm not gonna. I'm gonna move quite a bit up and down now, but I want to keep all of these equations so we can go back and double check things if there seems to be a problem. Okay. So what I might do at one stage is just go to the other side over here and write out the rest. Then I'm at least close to where I need to fill in these guys. All right, next one is point I. what kind of forces do we have at Y? So it's 1 up, 1 down. Alright. So point I. There's a force pulling up. It's a force pulling this way. Force pulling down. And a force pulling in this direction. It's not, there we go. There it snaps. So it is FAI and FBI. And then we have CI over here and which one is this? FHI, I think. HI, yes. Now, HI and FCI we don't know, but these two we do know. And FBI is equal to 30 kilonewtons. Oh, just one's direction. Let's quickly fill in that. It's 3 up, 4 to the side, 5 in total length. And FAI, that's the one I can't quite remember, is 20 kilonewtons. So they're all nicely in the positive direction, so this should be fun. Okay, let's start with sum of forces in the x direction, because I see that we have only one component of FCI in that direction. So sum of forces in the x direction is equal to 0, and we're going to add 4 over 5 of FCI and plus FBI. Now this is all relatively simple, so I'm going to skip over a few steps here. I'm just going to write FCI is therefore equal to negative 20 times 4 over 5. No, not 4 over 5, times 5 over 4. And then we get negative 25 kilonewtons, which makes sense if you look at it. Then in compression, because FCI is already pulling in the same direction as FBI, and we know that, oh, I messed it up. I should have times by 30, not by 20. I meant this. Oh, that's a silly mistake. It's negative 37. It's always good to go reason about these things then. Just double check. Okay, 37.5 kilonewtons, that makes more sense. Because it's already in this pulling in the same direction as FBI, so it needs to have the wrong sign. Otherwise there's no equilibrium. And it needs to be larger than FBI because it also has a Y component, but its X component needs to cancel out the FBI. Okay, great, so we are happy with that guy. And now let's do sum of forces in the Y direction. Then we have negative FAI. Let's make that negative a little bit bigger. Positive 3 over 5 FCI and positive FHI. Okay, and we want to calculate FHI, so we rearrange things and we get FHI alone. It's already positive as it is, so we move everything else to the other side of the equation. So we get negative FAI, so that's a negative but it now moves to this side, so it's in a positive, so it's plus 20. This one becomes negative, it's minus 3/5, but the value of CI is negative, so times minus 37.5. Let's get rid of that. So FHI and already see that it's going to be a big positive value. Should be 42.5 kilonewtons. And this is positive, so it's going to be a tension value. Well, this member is going to be in tension. And let's just see if that makes sense once again. FCI is in the wrong direction, as we discovered last time, so it's actually pushing down. And FAI is also pulling down, So we have a lot working against FHI. So it is in the right direction, otherwise there's no equilibrium. And it needs to be larger than 20 kilonewtons, plus something of CI. We get 42 kilonewtons, which is larger than 20, and some component of FCI. So I trust this value, it seems fine. Okay, let's go write these ones out as well. FCI, there is FCI. 37.5 kilonewtons, and this one is compression. And then we have FHI, which is all the way down here, and this one is 42.5 kilonewtons in tension. Okay, great. So we have another one of these points ticked off. Okay, next one. Sum of forces about point C. I'm going to do one last one down here, and then we're going to move to the other side. So let's look at point C. What forces does it have? As I can see, it was at least one down, one up, one load pushing into it, one this way, so like that, and then at least one this way. I think we're going to double check it now. Down into it, that way, that way. No, it's not up, it's skewed. There we go. Skewed away from it. Alright, now we are talking. Okay, this load is, I think the previous one was 40, so this one should be 30. I'm going to double check it now. 30 kilonewtons. This force is FBC. Check that load. This force is I think it's FCI, and I also need to check that one. And this one should be FCH, and this load should be FCD. Let's quickly go and check if I got all of that correctly. CB, CI, CH, CD. And the load is 30 kilonewtons. Great. Now I just have to go and see what BC was. BC was 52.5 kilonewtons in compression. So it is negative 52.5 kilonewtons, and CI was negative 37.5. Negative 37.5 kilonewtons. Great. And this is now point C. Did I write I? No, I did not. That is not good. This was point I. Okay, let's do sum of forces. Which one are we going to do first? We'll do sum of forces in the Y direction for a change. Sum of forces in the Y direction is equal to 0 because this one only has, this FCD only has one component in the Y direction. Then I'll leave it like that. Try to make sure that everything is in view for you guys. Okay, in the Y direction. Oh, I need these little triangles just to help me out. This is 3 down and 4 that way, 5 over here. Okay, now we can go specify things. So let's start off with FCD, and it is in the positive Y direction, so 3 over 5 times FCD. Then minus, let's do CI next, minus 3 over 5 FCI. And then negative FBC. Okay, and we can rewrite that as FCD, and we times by 5 over 3 on both sides. And this guy has moved to that side, so now it's a positive FCI because we times by 5 over 3. And plus 5 over 3. I should actually just write its value. Why do I keep writing FCI? FCI minus 37.5. So minus 37.5. So we have FCI, and then this one minus 52.5. Then FCD. FCD is then equal to minus 57.5 minus 5 over 3 times 52.5. So I'm getting minus 125 kilonewtons. And that means it's in compression. Now, quickly go check if this makes sense. FCI and FBC are both in the wrong direction, so they're actually both pushing upwards. That means that FCD cannot be in the positive, cannot be in tension. It needs to push downwards to counter those two forces. And there's two forces working against it, so it should be a bit larger than 52.5, and we got 125. No, yeah, it should be a lot larger than 52.5 because it only has a partial component in the Y direction. Yeah, that makes sense. No, it should be quite a bit larger than 52.5, about double, and it is about double that in magnitude. So yeah, now I'm happy with that answer. It makes sense to me. All right, let's go and do sum of forces in the X direction. Here's 0. Sum of forces in the X direction, and we want to calculate FCH. FCH, but it's in the negative direction, so we put a negative there. And it also has minus 30 that side, and both these are also pulling in the negative direction, so it is minus 4 over 5 FCD minus 4 over 5 FCI, I think. Yeah, CI. Then we go and rearrange this thing a little bit, and we get FCH is equal to, we put it that way, so all these are going to stay the same because this is negative, minus 30 minus 4 over 5, and the value for FCD is minus 125 minus 4 over 5, and the value for FCI is minus 37.5. Therefore, FCH should be equal to, and it is minus 30. It should be 100 kilonewtons. This one will probably be a little bit harder to see intuitively because there's quite a lot of forces acting in the y direction in this case, or in the x direction. Sorry, I misspoken. But let's try. We see that FCI and FCD are both in the wrong direction. So they're actually pushing in the positive x direction. And FCD is quite large, and FCI is not that small either, or they're both larger than this 30 kilonewtons, but they only have components in that direction. So still we would expect that the sum of FCD and FCI is significantly larger than the 30 kilonewtons. So FCH should be in the right direction, but it's a little bit difficult to estimate its magnitude. But I'm going to assume that everything seems to be in order. It doesn't seem to be impossible to me, the value that I'm getting. And then we have a value in tension. Okay, let's go at these two as well. So FCD, and we do loop in. FCD is 125 kilonewtons, and that is compression. And then FCH is 100 kilonewtons in tension. Let's just double check that. FCH 100 tension, 125 compression. Okay, we are making good progress at the moment. So point C is done as well. Now let's move over to point D. And I'm going to start on this side now. So point D, it has a force pulling this direction. It has a force pulling down and a force pulling this way. And this is a little triangle, 4 in the x direction, 3 in the y, and 5 in total length. And this is point D. This is then FCD, which we calculated. This should be FDH. And this one should be FDG. And I think we also have a load on that point. Yes, a 50 kilonewton load. And this is exciting because now we're actually getting to comparing some values. 50 kilonewtons. And FCD was not small, 125 in compression, so that's negative 125. Okay, but this is exciting because FD DG is actually, no, I made a mistake. It's not G, it's E, of course. E is the next letter in the alphabet. Well, it kind of makes sense how they arrange these notes, but anyway, it's not that fun. Okay, FDE is one of the first values that we actually did calculate over here. So we're expecting 100 newtons in compression. So if we get negative 100, then we should be fairly good to go. Then it would appear that we are on the right direction, because that's what we calculated previously. But we'll see, we'll see. Okay, which direction are we going to go in first? We know CD. We do, oh, they're both in nice directions. Okay, so we'll do, let's go X direction first. Go check immediately if we're far off or not. Positive, and it's equal to 0, which is equal to negative FDE plus 4/5 FCD. Great. And I think it's going to be correct. It should be correct. Okay. We rearrange this to get FDE on the other side, and it's going to be equal to 4/5, so this one stays on this side, times negative 125. Ooh, I can already feel it is correct. It's always a problem with these guys. These problems tend to get out of hand. You make one mistake somewhere down the line and then everything else is screwed up because you're using the values again and again. So I'm really happy that it seems that that is not a problem in this case. So it's 125 times 4/5. It's a negative 100 kilonewtons. I am really happy about this. Negative 100 kilonewtons, and that is compression. Okay, let's now do the y direction as well. Sum of forces in the y direction is 0, and it is equal to, okay, negative 50. And then negative FDH, and then negative again, negative 3/5 FCD. Okay, then we rearrange these guys to get FDH alone, and it's going to be equal to negative 50. Negative 3/5 times negative 125. The FDH is then equal to negative 50 plus 3/5 times 125. It should be equal to 25 kilonewtons, and this is then in tension. Okay, now let's quickly also go and reason about these guys, see if we agree with the values that we get. And let's start off with FDE. CD is in the wrong direction, so it's actually pushing in the negative x direction. So FDE has to have the wrong sign already. It needs to be in compression because it needs to push against D to counter the FCD force. And it also needs to be smaller than FCD because FCD only has a component in X, it's not entirely in the X direction, and FDC is. And we get 100 kilonewtons, and that fits the description that we're seeking for. All right, and FDH. We have the 15 kilonewtons pushing down. And then the FCD is actually also pushing up. And it is quite a large force, but it also has a component, so we're expecting a relatively small value in this case. FCD looks like it could easily overpower this 50 kilonewton because it has a magnitude of 125. So I'd say there's a good chance that FDH will be positive. When we solve for it, it should be in tension, helping the 50 kilonewtons reach equilibrium against FCD. So a value of 25 kilonewtons seems very reasonable to me. I'm going to be happy with that. Okay, let's go write these guys in. So the first one is 100 kilonewtons in compression. So it's 100 kilonewtons in compression, and this one is 25 kilonewtons in tension. And this value is exactly the same as we got last time, so I'm really happy about that. I'm gonna have tick marks all over this. I have the ED here and DE here, but it's the same force. I just didn't use alphabetical order in the previous video, but okay. So now we only have 2 points left. So D is done. H is next. Okay, H. So over here, so it is up, side, and okay, this one has a lot going on in it. And here we're going to check the other two values that we want to compare to. So this is also exciting. It has a force pulling up potentially, another one pulling down, to the right, to the left, and in this quadrant. And we have to be careful about this direction. This is point H, and this direction is 4 in the X direction, 3 in the Y, with length being 5 then. Okay, now we just have to check them, see if they are all in the right place. I'm thinking this force should be FCH. This one should be FDH. I think this is then FEH. This should be FHI. We should have calculated this one, and this one in previous steps. And this guy should be F was a GH. That's right. Okay, DH. What is DH? DH is 25. Tension, so it is a positive value. CH, let's go check. CH is 100 in tension. Okay, we have nice positive values for this step. 100 kilonewtons. And then HI. HI, that's all the way down here. 42.5. 42.5 kilonewtons. Okay, let's start off with the y direction. Y direction has FDH plus 3 over 5, one of the forces that we're looking for, FGH. No, not GH, FEH. I'm going to check it now. FEH, I am correct. Okay, and then last one acting in the y direction is FHI. And this one is pulling it down. FHI. So we can rearrange this equation to get F, what are we looking for? EH, right? Yes, EH alone, FEH. And then it's equal to times 5 over 3 times the two forces that's in here. FDH is 25, but it is moved to this side, so it's negative 25. This one is now positive, so we're going to just write the value, plus 42.5. And then I am moving on, FEH, negative 25 plus 42.5 times 5 over 3. So that is 29.1. And I'm going to write it in 4 significant figures just over here. Kilonewtons, and it is in tension. Now, magnitude wise, it seems to be exactly the same as what we got previously, and it's also in tension. So hey, we seems to have been going strong this round. Okay, and let's just reason about if that also makes sense to us. EH. So we have DH is 25 kilonewtons, pulling up, okay. And FHI is pulling down with 42.5 kilonewtons. So FEH should be in the right direction. It's a component thing, so it only has a component in the y direction. So it's difficult to say exactly how large it will be, but we know that the direction is correct. So I'm fairly confident to say that this should be I'm happy with the value that we got. It should be fine. Okay, now for the x direction. Sum of forces in the x direction. And this is also in 0. Sum of forces in the x direction. Now we have, let's put it all in. We want to calculate FGH. So minus FGH, because it's pulling in the negative direction, plus FCH. Okay, we have those two, and then it's also FEH with a component, and it's pulling in the negative direction, so minus 4 over 5 FEH. Okay, then we rearrange the equation to get FGH is equal to FCH, and CH is 100, if I remember it correctly. Yeah, it's 100. And this guy is minus 4 over 5 times 29.1667. Then FGH. It's going to be 100 minus 4 over 5 times 29.17, not 7, 667. So we get 76.66 66 newtons, kilonewtons. I think we have like a decimal off, but that's probably due to the amount of significant figures that we used. And it's 76.67. I think last time we got it to 76.66667. And now it's 66666. But anyway, that's like so small off. You can clearly see that it's the same value. And this one is also in tension. So we got exactly the same values for these points. So I'm really happy about that. That means that we were thorough in our calculations. And I'm not even going to double check this because we got all the exact same values, calculating it in a different way, so it should all be fine. I don't have a lot of doubt, and we've been checking everything up till now. So this is enough of a sanity check for me for this last one. I'm not going to scrutinize it like the others. Okay, then we can rewrite it as GH is down here, 76.67 kilonewtons in tension. And we have another one, FEH. This one is 29.17. Kilonewtons, also tension. And I am very happy with this answer and this answer. And now we only have two forces left that we need to go calculate. So I'm going to switch back to the black pen. So we have H now. And then we only have F to still go and calculate. And the free body diagram for that will look as follows. And this is the force FEF. And this one is the force FG. And this is the reaction force, but I'm just going to write in the values for that. This is this one, 57.5 kilonewtons. Okay, I write it, yeah, I did put the H over there. Okay, let's do some more forces in the Y direction. Is equal to 0 is equal to 57.5 plus, and I forgot to add a little triangle over there. This is 4 in the X direction, 3 in the Y direction, and 5 in length. So it is plus 3 over 5 F E F. Therefore, we can just write down the answer now. I can already see that it's in the wrong direction. It will be a compression force because this guy is pushing up and this guy is pulling up, and that cannot be. So FEF is going to be negative 5 over 3 times the value of that reaction force, 57.5, and then we get minus 98.833 kilonewtons, which means this guy is in compression. Okay, last force, x direction, sum of forces in the x direction is equal to 0. Then it is FG plus 4 over 5 FEF. And we can go rewrite this equation a bit, and we get that FG is going to be equal to negative 4 over 5 times negative 98.8333. Then FG, let me just double check that, 98.833, great. Then it's going to be a positive value, 5 times 98.833. I typed that in not wrong, 98.8333. Then we get 79.0666 kilonewtons, which means it is in tension. Okay, so now that we have that, it is all done and dusted. Let's just double check. FEF is in the wrong direction. It's actually pushing F in the negative x direction. So FFG is in the right direction. It needs to be smaller than FEF because FEF only has a component in the x direction, and FFG is entirely in the x direction. And did we get that? Absolutely. So we are happy. Now we just have to quickly go and write these guys down as well. 98.83. It is using this guy. 98.83 kilonewtons, and this is compression. And this guy is 79.07 kilonewtons of tension. And now we have done all of the forces. Now we know all of the forces in this truss system, and we should be able to do stress and strain analysis if we really wanted to on this system. Now, strain is going to be a little bit harder, but stress is no problem with the stress. Okay, and then we can also look at things like buckling for the compression forces and stuff like that. But it is all good. We have done all of it, all the forces. Okay, I'll see you next time.